Deep learning essentially means that we do machine learning and make use of deep neural networks. In this video, we briefly explain the main building blocks in a deep neural network. It's important to note that a neural network is just a function. Thanks to the universal approximation theorem, we know that, given certain regularity conditions, neural networks with enough neurons can approximate any function. That is, neural networks are parameterized functions that are very flexible. The most basic type of network is a feed-forward neural network with a number of different layers and a number of neurons in each layer. First, we have an input layer where we plug in the data. After that follows a number of hidden layers and finally an output layer. The term hidden refers to the fact that we don't observe the values of the neurons in the hidden layers. When counting the number of layers, we do not include the input layer since that does not have any free parameters. We use capital L to denote the total number of layers, where capital L is the number of hidden layers plus 1, which is 3 in this example. We use A superscript brackets J subindex I to denote the ith neuron in layer J. For notation, we often write xi as A0i, even though we do not view xi as a neuron. Please note that even though this example has 3 neurons in each layer, the number of neurons usually varies between different layers in the network. Also, most deep neural networks are much deeper and wider than the network illustrated here, and it's common to have networks with millions of parameters. We usually refer to the value of a single neuron as the activation, which is also why we are using the letter A to denote it. To compute the activation of a single neuron, we first compute a variable z, which is an affine function of the activations in the previous layer. To compute zij, we take the sum of a bias, bij, and a weighted sum of the activations in layer j-1, that is, a summation over I of wij-1 times aij-1. The variable z is then passed through a nonlinear function g. The nonlinear function g is here called an activation function. It's important that g is nonlinear in order for the neural networks to become a flexible family of functions. Once we've decided upon an architecture, the biases and weights are the main parameters in our neural network. Like I mentioned previously, it's common to have millions of weights in a network. Fortunately, we don't select the weights by hand. Instead, we generally use our data to select these parameters. As of 2019, the rectified linear unit is by far the most commonly used activation function for the hidden layers. A rectified linear unit, or ReLU for short, takes the maximum of the input variable and 0. This means that whenever the input is negative, the output is 0. If the input z is instead positive, the output is z. The output layer is a bit special, and the choice of output activation function depends on the task we are trying to solve. For instance, if we are doing regression, that is, if we are trying to estimate something, we normally use the identity function g of z equals z, or if we know that the output variables are always positive, we might use a ReLU activation. Another very important activation function is the softmax function. We almost always use softmax for multi-class classification problems, such as image classification or to predict the next word in a sentence. In the softmax function, we first take e to the power of all the different zi variables. Note that the variables a tilde I are all positive. In a second step, we then compute ai by normalizing the a tilde variables. We note that the output variables are normalized to sum to 1. This means that we can think of them as probabilities, and we usually train our networks such that ai should approximate the probability of class I given the input variable x. We also note that the softmax function actually depends on all the z variables, since the output variables are normalized across the different output neurons. In this video, we have limited our description to feed-forward neural networks. However, many of the other network architectures, such as the convolutional and recurrent networks, can be thought of as feed-forward neural networks. In this sense, the networks used for image classification are very closely related to what you've seen here. One common adjustment is that many of the edges are removed. This gives the same result as setting the corresponding weights to 0. Also, we often use something called weight sharing, which means that some of the weights are constrained to take the same values. By introducing these two adjustments in a reasonable and careful manner, we can transform our feed-forward neural networks to, say, a convolutional neural network. Of course, deep learning is a very active research field, and there are tons of other adjustments and novel architectures proposed on a regular basis. Unfortunately, it's beyond our scope to describe any of these in detail.